If you've ever wondered what Earth is like during a mass extinction, the answer is simple. Just look out the window, wherever you are. The transformations caused by human beings have changed the planet in profound ways, wiped out thousands of species, and destroyed entire ecosystems. In this documentary, we'll travel into the past to witness moments in the history of life that are just as decisive as the one we're living through now. We'll look at the 5 great mass extinctions and many other, smaller but equally important ones, until we can understand the 6th great extinction unfolding today. Get ready to go back more than 4.5 billion years and witness some of the most dramatic episodes in all of biology. In the end, we'll have a clearer view of what is happening right now and of how Earth might recover after the extinction we ourselves are causing. Climate change, ocean acidification, habitat loss, and the extinction of large animals are all phenomena that have happened before in other eras of biosphere instability. The difference is that this time, we are the cause. This is the story of the mass extinctions of planet Earth. Welcome to the Hadean Eon, shortly after Earth first formed. In the young oceans of that time, hot, dark, and chemically chaotic, life emerged. It's possible that on the surface of those hydrothermal chimneys, a thin layer of lipids formed that, when heated, produced tiny bubbles. These bubbles could trap amino acids and other molecules floating in the water, creating little compartments where the chemistry of life began to organize itself. This is not yet a living cell, but it already has something very important: a phospholipid layer separating an inside from an outside. And inside, there is a chemical broth rich in amino acids, just like in real cells. These structures are called protobionts, a model of how life might have begun to organize itself more than 4.3 billion years ago. Curiously, Earth's first mass extinction may have happened shortly after life originated, although for now, this idea is only hypothetical. We know that the simplest forms of life we see today are bacteria and archaea, known together as prokaryotes. Their cells are usually small and simple compared with eukaryotic cells, which are those of protozoa and multicellular organisms like fungi, plants, and animals. By far, prokaryotes are the most important organisms that have ever existed. Thanks to their enormous variety of chemical tricks and their colossal biomass, they can change the chemistry of the seas and the atmosphere. As soon as they appeared, they immediately began to modify the composition of the oceans and the air, and it's possible that they destroyed the very special conditions that had allowed life to arise in the first place. The brutal, global success of those first prokaryotes may have altered ocean chemistry so much that it completely wiped out the even simpler forms of life that preceded them and gave rise to them. That may be why it is so difficult today to understand how life began and what those first beings were like. They didn't survive the world they themselves helped create. And with this first possible extinction, tied to the great explosion of prokaryotic life in the oceans, begins what we call the Age of Bacteria, the longest phase in all of Earth's history, which lasted for more than 4 billion years. This age is divided into 2 great eons, the Archean and the Proterozoic. For more than 2 billion years of the Archean, there were no plants, no animals, no fungi, no complex eukaryotic cells. And even if they had appeared, they would not have survived. Levels of dissolved oxygen in the water ranged from 0 to almost negligible values. In the atmosphere, it was even rarer. There was practically none. The oceans, loaded with iron and sulfur, would have been a greenish turquoise color, with possible purple zones where bacteria accumulated. The sky would have shown shades between beige and greenish. Overall, the planet would have looked almost alien. In these deeply anoxic conditions, that is, without oxygen, bacteria that used sulfur and methane thrived, known as purple bacteria. These bacteria carried out a type of photosynthesis that only works in the absence of oxygen. Many of them produced hydrogen sulfide as waste, a toxic gas with the smell of rotten eggs, capable of killing a mammal even at very low concentrations. Methane was also a very common product of many metabolisms of the time, just as it is today, and it acted as a powerful greenhouse gas. On that stifling Earth, there was no fire because there was no oxygen to feed combustion. This reminds us of how incredibly reactive oxygen is. What there was in huge quantities was water vapor, methane, and carbon dioxide in the atmosphere, creating a gigantic greenhouse effect that kept water liquid on the planet's surface. In the Archeans, shallow coastal waters rose over long periods the largest living structures on the planet, stromatolites. These are structures formed by the interaction between layers of photosynthetic microorganisms and sediments moved by waves and tides. These biofilms were thin layers of bacteria that colonized the surface to capture light, with no herbivores around to eat them. When one layer was covered by sediments, a new one formed on top, and the lower layers mineralized. Over time, this produced structures of varied shapes with a very characteristic laminated pattern. They often had dome-like forms, reminiscent of termite mounds. They still exist and continue to form today, though they are much rarer. One of the most famous places where they occur is Shark Bay in Australia. Today, purple bacteria that once dominated the hot Archean seas live only in very specific environments, and when they spread too much, they can be extremely harmful to oxygen-using life forms like ours. In the Archean, however, roles were reversed. Cyanobacteria, those that carry out green photosynthesis and produce oxygen, were the extreme life forms. Their proliferation released oxygen, a poisonous gas incompatible with the life of purple bacteria. These two kinds of photosynthesis have been waging an epic battle for billions of years. Right now, we are winning on the side of oxygen, and the turning point came in the transition from the Archean eon to the Proterozoic eon, about 2.5 billion years ago. Cyanobacteria multiplied especially along the equatorial belt and eventually came to dominate the planet, transforming Earth into something much more like the world we know today. The enormous amount of oxygen they began to produce first dissolved in the oceans and reacted with dissolved iron, oxidizing it and forming oxides. In essence, rust. For millions of years, that stained the seas red. Oxidized iron does not dissolve well in water, so it accumulated and settled on the seabed, layer after layer. Over time, this formed the so-called banded iron formations, which today are major chemical fossils of the planet's great oxygenation event. When oxygen began to escape from the oceans into the atmosphere, it stopped being a rare gas and became one of its main components. The chemistry of the air changed completely, and with it, the climate also changed. Oxygen destroyed many methane molecules, which until then had been the main greenhouse gas. As methane disappeared, the planet's temperature dropped dramatically, and the first and most intense ice age in Earth's history began, the Huronian glaciation. The entire planet froze from the poles to the equator in what we call a snowball Earth event, directly related to the Great Oxygenation and the so-called oxygen catastrophe, a mass extinction that, paradoxically, helped create the world we inhabit today. But that same oxygen eventually formed the ozone layer, which blocks much of the solar and cosmic radiation and makes Earth's surface much safer for complex life. It is also responsible for our skies being blue. This ice age lasted more than 300 million years, a period longer than the entire time that separates us today from the first dinosaurs. At last, Volcanic eruptions released enough CO2 into the atmosphere to strengthen the greenhouse effect and melt the ice, still under the light of a younger, cooler sun. The new conditions of the Proterozoic eon, with a planet already dominated by cyanobacteria and a different environment, allowed the emergence of the first eukaryotic cells, probably the single biggest leap in the entire history of life. We know that the last common ancestor of all animals lived more than 800 million years ago, something that fits with sponge fossils of the same age. That indicates that animals already existed in the Tonian period of the Neo-Proterozoic era of the Proterozoic. However, animals only became large, complex, and abundant almost 300 million years later, during the famous Cambrian explosion, because throughout that long prior interval, Earth was like an unpredictable climate time bomb, with abrupt, extreme shifts that made long-term stability difficult. About 720 million years ago, Earth's thermostat spun out of control again. New increases in oxygen triggered another snowball Earth episode during the cryogenian period. It's possible that even then there were ice-free zones near the equator where animal life could have survived, along with many photosynthetic life forms that may even have thrived within the ice itself. Even so, life in general, and animal life in particular, managed to survive this extreme glacial episode. When the cryogenian ended, the Ediacaran period began, the stage that led to the so-called Avalon explosion, the first major expansion of multicellular life in history, about 570 million years ago. But the creatures of the Ediacaran are so strange that understanding them has been almost impossible. There were flat, fractal patterned forms over a meter long, with no clear mouth or sensory organs, like Dickinsonia, a member of the so-called vendobionts. Today, most specialists think they were animals, although others propose they were an entirely separate multicellular group that is now completely extinct. There were also enormous sea feathers, like Charnia, which extended down into the deep ocean. They fed by filtering organic particles from the water and grew very slowly, with no need to worry about predators. The Ediacaran is sometimes compared to a kind of evolutionary Garden of Eden, a time before the fall in which everything lived in harmony. It's a nice image, but not entirely accurate. We know that many of these life forms were the planet's first herbivores. They fed on biofilms and carpets of algae that covered the shallow seafloors where sunlight could reach. Most animals still had soft bodies, without skeletons. We know about them because those algal carpets helped stabilize the sediment and made fossilization easier. Toward the end of the Ediacaran, the first inventors of organized skeletons appeared. Skeletons arose independently in several animal groups at roughly the same time as a response to a shared evolutionary pressure, a large influx of calcium into the oceans, the result of rock erosion. That's how some of the first complex animals with calcium carbonate skeletons appeared, such as Corumbella, which lived in what is now Brazil at the end of the Ediacaran and is interpreted as a cnidarian, the group that today includes corals, anemones, and jellyfish. Corumbella lived alongside other organisms like Claudina and Namacalathus, small, sessile creatures fixed to the sea floor, only a few centimeters tall but capable of building highly organized segmented skeletons. A hole found in a Claudina fossil suggests that these skeletons may have served as protection against some of the first predators in history. Exactly who those predators were remains a mystery. These Ediacaran communities lasted for tens of millions of years until they suffered a little-known mass extinction that almost completely replaced the Ediacaran biota with Cambrian fauna. The change was so abrupt that we call everything before the end of the Ediacaran Precambrian. From that point on, the ecological roles, predators, prey, scavengers, filter feeders, that with variations still exist today, were established. The appearance of skeletons triggered a kind of evolutionary arms race that forever transformed ecosystem structure. With them, the predator-prey relationship took full shape, a key evolutionary force that drove the Cambrian explosion of anatomical and ecological complexity. The new animals with skeletons began to swim, to hunt, to burrow into the sea floor, and to dig through the sediment. This destroyed the algal carpets and the conditions that had previously favored the fossilization of soft-bodied organisms. At the same time, skeletons fossilized much more easily, which gives us the false impression that during the Cambrian explosion, highly complex animals appeared all at once. In reality, even that event unfolded in several phases over millions of years and was preceded by more than 300 million years of animal evolution that we can barely see in the fossil record. That evolution happened in a world of small, soft-bodied animals, during a phase of global glaciation in which very few fossils formed, and many of those that did were later destroyed. During the Cambrian, the top predators were arthropods like Anomalocaris, with a circular mouth and two front appendages shaped like claws, guided by highly developed eyes. The ancestors of vertebrates, like us, were nowhere near the top of the food chain. They were tiny creatures such as Pikaia, which was barely 1 centimeter long. The dominance of invertebrates, arthropods, mollusks, and brachiopods, continued into the Ordovician period. At this time, the first giant filter feeders evolved, such as Aegirocassis, which could reach about 2 meters in length, something like an invertebrate whale that fed by filtering small animals and organic matter suspended in the water. The first large Ordovician predators also appeared, like Camarasaurus, a cephalopod around 9 meters long that sat at the very top of the food web. Among the smaller but equally fearsome predators were the Eurypterids, known as sea scorpions. During the Ordovician, the most common fish had no jaws and were not very large, but their big moment would arrive later, with the beginning of the so-called Age of Fishes. The end of the Ordovician is marked by what is considered the second most severe mass extinction of the classic Big Five. More than 80% of species disappeared in the extinction between the Ordovician and the Silurian. An intense glacial system took hold when the continents drifted toward the South Pole, altering global ocean currents and triggering deep climate shifts. As more ice piled up above sea level, ocean levels dropped dramatically, destroying the shallow seas where most animal life lived. It's possible that coral reefs took more than 100 million years to regain the complexity they had before this extinction, which happened about 445 million years ago. It was the first of the 5 great mass extinctions. To reach the second of those 5 great extinctions, we jump ahead to the end of the Devonian, about 372 million years ago, to a very different Earth. In the oceans, now dominated by fish, swam enormous placoderms like Dunkleosteus, comparable in size to modern orcas. There were also cartilaginous fish, ancestors of sharks and rays, and many lineages of jawless fish, although these were already in decline. On land, plants had spread and formed the first forests, very different from today's. They were dominated by seedless plants like ferns and giant horsetails, along with some of the first true seed plants. In swamps, deltas, and marshes, a group of fish lived an amphibious lifestyle. They could breathe air, but their limbs were still not very efficient for moving on land. They were the ancestors of tetrapods, very similar to Tiktaalik. We know that this huge diversity of animals was almost wiped out by the Devonian extinction. Only the lineage that would eventually give rise to amphibians survived. But if that mysterious biodiversity crash had never happened, it's possible that animals similar to Tiktaalik would still exist today, in the same way that the coelacanth still lives and retains an anatomy very similar to that of a much older ancestor. In any case, most jawless fish disappeared, as did all placoderms, including Dunkleosteus. Marine environments were hit the hardest, but the cause may have begun on land, with a genuine revolution in the plant world. Toward the end of the Devonian, seed plants began to spread into drier regions where seedless plants could not live. Their roots greatly increased soil erosion and started forming layers of soil rich in organic matter. This may have sped up rock weathering and increased the amount of nutrients rivers carried to the sea, fueling enormous algal blooms and causing episodes of eutrophication. In a eutrophication event, so much organic matter accumulates that its decomposition consumes almost all the oxygen in the water, making it unbreathable for many marine animals. That may be why the only tetrapods that survived the Devonian extinction were those best adapted to life on land. And this would not be the last time that plant evolution changed the planet so profoundly that it destabilized the entire ecosphere. Next comes the Carboniferous, a period stretching from about 359 to 300 million years ago. A warm, very humid world covered by almost continuous forests. On the floor of those waterlogged forests lived arthropods of many sizes and numerous amphibians, in an atmosphere with more oxygen than today's. Among them were Arthropleura, one of the largest arthropods known, a millipede that could reach almost 3 meters in length, and Meganeura, a predatory dragonfly with a wingspan of more than half a meter. In this time, amniotes arose from within the amphibian line, the first vertebrates capable of reproducing on dry land. Their success was due to a major evolutionary innovation: eggs with shells and internal membranes that retain moisture but allow gas exchange, unlike the soft eggs of amphibians, which need to develop in water. Carboniferous forests were made up of some of the first plants to produce lignin, such as lepidodendron, which could grow to more than 50 meters tall. Lignin is now a key component of wood. It provides a combination of rigidity and flexibility that these gigantic lycophytes exploited to the fullest to support their enormous size. Lignin was a new fibrous molecule on the planet, and there were almost no microorganisms capable of breaking it down quickly and efficiently enough to keep pace with forest growth. As a result, trees grow by trapping carbon from the atmosphere and storing it in their trunks and branches. When they fell, they did not fully decompose before being buried under new layers of plant debris. Under these conditions, rocks very rich in organic matter formed, such as coal, the same fossil fuel heavily used today and the one that powered the Industrial Revolution. But whereas today the problem is that all that fossil carbon is returning to the atmosphere, at the end of the Carboniferous, the opposite was happening. As trees grew and accumulated, they absorbed CO2 and removed it from the air, turning down the planet's thermostat to a critical point. This is known as the collapse of the Carboniferous forests, the moment when those forests quite literally ate themselves and profoundly altered the carbon cycle. The consequence was the Karoo glaciation about 300 million years ago, a huge ice cap at the South Pole that covered much of what is now Brazil, which at the time lay much farther south. At the same time, the continents were coming together to form Pangaea, a supercontinent that made it harder for ocean moisture to reach the interior. All this marked the end of the tropical Carboniferous forests and the beginning of a colder, drier world, the Permian. In this new setting, the amniote tetrapods, which during the Carboniferous had learned to reproduce in dry environments, came to dominate the land for the first time. Ecosystems began to look more like those of today, with four-legged animals competing for the main terrestrial niches. These first Permian amniote communities looked very little like modern fauna and were divided into two major groups: the sauropsids, which would give rise to all reptiles and birds, and the synapsids, which would give rise to mammals. During the Permian, both lineages diversified, but the synapsids were the largest and most abundant. The pelycosaurs at the beginning of the period, the oddly skulled dinocephalians, which thrived in the mid-Permian as herbivores and carnivores, the gorgonopsids, top predators of the late Permian with saber-like teeth and a huge gape, and the small dicynodonts with beaks and tusks adapted for digging and living underground, like Lystrosaurus. Strange as it may seem, Lystrosaurus is more closely related to mammals than to reptiles, although it belongs to a branch of synapsids that is now completely extinct. The Permian ended with the third of the 5 great mass extinctions, and by far the most severe of all, known as the Great Dying. In this event, about 252 million years ago, a series of devastating geological processes ravaged the planet and wiped out more than 90% of species. If something existed before the end of the Permian, likely it did not exist afterward. A classic example is the trilobites, which appeared in the Cambrian 300 million years ago and vanished forever. It all began with an immense eruption of basalts in the region that is now Siberia, which released enormous amounts of greenhouse gases and sulfur compounds into the atmosphere over millions of years. The excess carbon in the atmosphere may have caused an increase of more than 10 degrees Celsius in the global average temperature, subjecting the planet to unbearable heat waves year-round. Dissolving into the oceans, CO2 combined with water to form carbonic acid, acidifying the seas and making life difficult for organisms with calcareous shells and skeletons. Climate change was so abrupt that the oceans almost stopped mixing and effectively rotted. Eutrophication events occurred, vast oxygen-free zones formed, and there was an explosion of purple bacteria that released hydrogen sulfide, poisoning the water and the atmosphere. The combination of acid rain, extreme warming, collapse of marine food webs, poisoning by toxic gases, and the configuration of Pangea, which worsened continental climates, pushed animal life to the brink and almost erased it, forever transforming the evolution of complex life. For more than 5 million years, Earth was an empty, hot, hostile, and poisonous planet. This disaster marks the end of the Paleozoic era and the beginning of the Mesozoic era, known as the Age of the Dinosaurs. Many of the animals that managed to survive this third great extinction, the Great Dying of the Permian, were species that could burrow and take refuge underground, temporarily protecting themselves from extreme heat and brutal drought. This event closed the Permian and opened the Triassic 252 million years ago. The Triassic marks the beginning of the Mesozoic, the age of the dinosaurs. But they were not the first animals to recolonize the planet after the extinction. The descendants of those small, lizard-like diapsids of the Permian diversified into many strange forms, such as Etosaurus, which resembled armored crocodiles but were herbivores. However, during the first few million years of the Triassic, before Earth had fully recovered, the most common land animals were not dinosaurs but synapsid cynodonts, like Lystrosaurus. They spread across almost the entire planet like a plague and became the most abundant terrestrial vertebrates in the world. For a brief time at the beginning of the Triassic, Earth was literally the planet of Lystrosaurus. Some of their descendants grew as large as elephants, such as the impressive Lysowisia, the first giants of the dinosaur era. Except that, ironically, they were not dinosaurs but synapsids, distant relatives of mammals. And that was just the beginning of a huge variety of strange animals that dominated the Triassic. This period may have been the second greatest animal diversification event in history, a burst of new life forms proportional to the ecological vacuum left by the Permian extinction. When Earth is left empty, ecosystems are less competitive, and different evolutionary lineages can experiment with new resources and new body plans. These post-crisis moments are often among the most fertile for evolutionary innovation, because the risk of trying new things is lower and almost everything gets a chance. By contrast, when ecosystems are already well established, the roles of producers, herbivores, and predators are very well defined and hotly contested. In those stable times, one of the main evolutionary forces is the pressure to stay as you are. If a species has perfected its way of life over millions of years and dominates its niche, it usually does not benefit from changing too much. Evolution continues, but it's less visible. It happens more in genetic changes than in drastic body transformations. Even so, the great evolutionary adventure of the Triassic was interrupted by the fourth great mass extinction at the boundary between the Triassic and the Jurassic. As Pangaea began to break apart, another huge amount of greenhouse gases and sulfur compounds was released into the atmosphere, acidifying the oceans once again and causing global-scale desertification and aridity. These volcanic eruptions were nothing like today's. They were vast regions of crust where it became very thin and mantle heat rose up, generating immense volumes of volcanic rock. Today, these deposits are known as the Central Atlantic Magmatic Province. This was also one of the most severe extinctions, both on land and in the sea. All dicynodonts disappeared, including Lystrosaurus and Lysowicea, as did many branches of terrestrial archosaurs and bizarre marine reptiles. That's why Triassic animals seem so strange to us. Many of those forms lived for only a short time, trapped between two of the harshest extinctions in the history of life. Feinstein is that most Triassic creatures existed only in that period. The big winners of this mass extinction were the dinosaurs, which until then had usually been small generalist animals. They also had a very efficient respiratory system, ideal for the low oxygen levels of the late Triassic. In the periods that followed, the Jurassic and the Cretaceous, dinosaurs diversified and flourished in many different forms, in a world more humid and forested than the Triassic. Between the Jurassic and the Cretaceous, there was also a little understood mass extinction, as happens with many of the boundaries between geological periods. The geologic timescale is not arbitrary. It's based on important biological and evolutionary events that mark phases of major change and relative stability, coinciding with deep turnovers in fauna and flora. In those folds in time between one period and the next, some of the worst moments in the history of life tend to hide, followed by new worlds that rise from the ashes of the old. For more than 100 million years, dinosaurs dominated every continent and gave rise to many different lineages. Of all of them, only one survived: the birds. That's because at the end of the Cretaceous, 66 million years ago, the age of the dinosaurs ended abruptly when an asteroid struck what is now Mexico's Yucatan Peninsula. The Chicxulub asteroid was more than 10 kilometers in diameter and slammed into Earth at a speed far greater than that of a bullet. The combination of the dust cloud, the global fires caused by red-hot re-entering fragments, the gigantic earthquakes and tsunamis more than 100 meters high that swept across the Atlantic was a brutal blow to life worldwide, probably one of the worst days in Earth's history. But what really ended up suffocating and eliminating many of the large Cretaceous animals was the layer of dust that stayed in the atmosphere for decades and contaminated the surface and oceans for thousands of years. Without sunlight, temperatures plummeted. A long, dark, terrible winter began, eventually killing the non-avian dinosaurs that had managed to survive the initial impact. One of the main pieces of evidence for this impact is a sediment layer rich in iridium that appears all over the world. Iridium is very rare on Earth, but common in asteroids. Below that layer, there are enormous numbers of large dinosaur fossils. Above it, none. That line marks the end of the age of the dinosaurs and the last of the 5 great mass extinctions. In the 1980s, a crater more than 300 kilometers in diameter was discovered on the Yucatan Peninsula, the same age as the iridium layer. This coincidence finally allowed scientists to answer with considerable confidence the old question: why did the dinosaurs die out? It was one of the fastest and most dramatic extinctions in evolutionary history. One day, the world of the dinosaurs existed and thrived. The next day, it was gone. With the end of the Cretaceous, the Mesozoic also ends, and the Cenozoic begins, the so-called Age of Mammals. After hundreds of millions of years living in the background, in the dinosaur's shadow, mammals finally found a world they could make their own. But they were not alone. Several reptile species also survived, such as lizards, crocodiles, and turtles, and a single dinosaur lineage: the birds. Many of these survivors were tied to freshwater environments, probably among the ecosystems least damaged by the extinction. During the Paleogene, the first period of the Age of Mammals, many now extinct mammal lineages diversified and filled the available ecological roles. The Age of Mammals was in full swing. But that doesn't mean those animals looked like the ones we know today. One of the largest animals 50 million years ago was Uintatherium, a mammal from a completely extinct group with strange bony protrusions on its skull that gave it a very odd appearance. There was also Berylambda, which weighed nearly 700 kilos, just 5 million years after the dinosaurs went extinct. It was a pantodont, a member of a family of mammals that has completely disappeared, which only vaguely resembles modern animals. Among the top predators were the creodonts and mesonychids, which only superficially remind us of modern carnivores like dogs or cats. At that time, the world was still covered by dense forests, as it had been in the Cretaceous. But that situation would not last forever. Still in the Paleogene, around 34 million years ago, Earth began to cool slowly but steadily. At the South Pole, Antarctica, once covered in temperate forests teeming with life, started to endure increasingly harsh winters. Year after year, forests disappeared and life retreated from the continent. Around 23 million years ago, in the transition from the Paleogene to the Neogene, this cooling had changed the planet completely and gave rise to a fauna much more like the one we find familiar today. In this colder, drier world, vast savannas, prairies, and grasslands spread, favoring herbivores able to live in open spaces and feed on grass. This was when hoofed animals, such as artiodactyls, deer, cows, antelopes, and perissodactyls, horses, rhinos, became very diverse, large, and abundant. It was also the time when carnivores of the order Carnivora, cats, dogs, hyenas, and so on, consolidated themselves as the main predators in much of the world. In that era, Australia and South America were island continents, each with its own version of the Age of Mammals, true parallel evolutionary laboratories with their own cast of species. That's a story that could be told separately. Even within these main lineages, there were animals that today would seem almost nightmarish, such as the Chalicotheres, which looked like a bizarre mixture between a horse and a gorilla, or the many strange relatives of elephants, like Platybelodon, which had a shovel-shaped lower jaw. Submicid parda began to disappear about 2.5 million years ago, during a new extinction pulse, linked to the onset of the Ice Age we are still living in. Although it may be hard to believe, we are still in an Ice Age, defined geologically as any stage in which Earth has two poles covered by permanent ice, that is, when a stable cryosphere exists. This glacial phase is characterized by an alternation between intense, very cold glacial cycles and shorter, warmer, wetter interglacial cycles, like the one we are currently experiencing. During the strongest glacial phases, ice sheets advance thousands of kilometers, Sea level drops by tens or even hundreds of meters, deserts and savannas expand, and forests retreat and fragment. The glacial world, with its cycles of intense climate change, is a much harsher, more unforgiving place for most life forms, especially for large mammal megafauna. With the onset of this stage, dozens of mammal types went extinct, and the animals we now associate with the Ice Age appeared, such as woolly mammoths, adapted to much colder climates than those of their ancestors. During the Pleistocene, in this context of fragile ecosystems and rapid change, the human lineage that originated in Africa spread across much of the planet, adapting to all kinds of environments, even the most hostile. Until then, although humans had already dispersed through almost the entire world, they still lived as nomadic hunter-gatherers, rarely staying long in the same place and depending directly on the food provided by nature. Between 12,000 and 10,000 years ago, in the transition from the Pleistocene to the Holocene, the current interglacial began, a period with a milder climate, but accompanied by another extinction pulse that struck the planet's megafauna hard. On every continent, almost at the same time, a large share of giant animals disappeared, such as the last giant ground sloths of South America and the famous woolly mammoths of the Northern Hemisphere. Amid this period of change, humans invented agriculture and animal husbandry, and for the first time became dependent on a single region, growing crops and raising domesticated animals such as cattle. Thanks to these innovations, people began to settle along the banks of great rivers in the Fertile Crescent, and shortly afterward, people all around the world began to practice agriculture, build cities, and develop increasingly complex institutions. The role of humans in the extinction of Pleistocene megafauna is still hotly debated. Some scientists believe our hunting pressure was the main cause of the disappearance of many large mammals that were trying to adapt to the new Holocene climate. Others think we are not the only culprits and propose that agriculture may have arisen as a response to the scarcity of large prey in many regions. On a healthy Earth, there should be massive migrations of millions of large animals on every continent. The simple fact that today it is so difficult to see large animals, or almost any land animals at all, even in the most biodiverse countries, is a very clear sign that something is wrong. Today, almost all the planet's megafauna is made up of animals domesticated and controlled by us. On a healthier Earth, it would not be unusual to cross paths on a trail with a giant sloth weighing more than a ton. When we ask, why were animals in the past so big? Or, why does it seem like there used to be many more huge animals? The answer is this: we are living through a mass extinction. There was an initial pulse at the beginning of the Ice Age, about 2.5 million years ago, and another at the start of the current interglacial, about 10,000 years ago. Just 10 millennia ago, the largest animals in South America were giant sloths weighing well over a ton. Today, the largest native land mammal on the continent is the tapir, which weighs around 250 to 300 kilograms. Paradoxically, our dominance of the planet has both facilitated and worsened the extinction that began in the Pleistocene. We are a generalist, highly adaptable species that learned to take advantage of, and at the same time aggravate, the fragility of megafauna populations, starting from the end of the Ice Age. Like Lystrosaurus in its day, humans occupied a relatively empty, less competitive world, though more demanding from a climatic standpoint. We overcame that challenge as niche constructors, modifying the environment to suit our needs. But that was only the start of something even more serious: the extinction of the Anthropocene. This third extinction pulse, which has intensified over the last 250 years, is even more serious than the previous ones and threatens both the integrity of ecosystems and the stability of the glacial climate pattern to which Earth has grown accustomed over the last 2.5 million years. The planet runs the risk of leaving this ice age entirely. which would be catastrophic and highly destabilizing for our civilization. Human activity has driven extinction rates to levels thousands of times higher than the natural background rates of healthy ecosystems. Among today's main problems are uncontrolled emissions of greenhouse gases, habitat loss and fragmentation to make room for agriculture and livestock, and ocean acidification caused by the dissolution of polluting gases in seawater. All this is happening extremely fast on geological timescales. Processes that would normally take millions of years are occurring in decades, with an impact on life on Earth almost comparable to that of a meteorite. In a sense, we are haunted by the ghost of the carboniferous forests. We burn, for energy, the very same carbon that was stored in swamp plants 300 million years ago. It is the same carbon whose removal from the atmosphere triggered the Karoo glaciation and helped amniotes succeed. Naturally, this reality frightens us, especially the youngest among us, who will have to live with the consequences of these decisions for their entire lives. Climate changes are already here. Fires, droughts, extreme storms, pollution, and everything suggests that these phenomena will become more frequent and more severe. Even so, all is not lost. It is always worth fighting to preserve what remains of our fragile biodiversity, as long as we do not surrender to despair. The history of life shows that organisms can recover even from the worst crises, and life will surely do so again after the extinction we are now part of. Those who do not have their continuity guaranteed in times of great instability are large, dominant animals, like human beings are today. Life as a whole will find a way. The question is, will we? Subscribe to the channel, share this video with your friends, and thank you so much for making it all the way to the end.